Welcome students to this next session on industrial metallurgy. This is session number 39 and we'll continue our discussion on the iron carbon systems. In this particular session, we'll talk about the invariant reactions which occur on the iron cementite equilibrium diagram. In other words, the reactions which occur in the iron carbon systems of steels and cast irons. Invariant because when these reactions are taking place, there are 0 degrees of freedom available with the materials system. So nothing can be changed, nor the composition, nor any other thing, nor the relative weight of the constituent phases which are participating in the reaction. So in a sense, there are 0 degrees of freedom, and for that reason, these reactions are invariant reactions. Also under equilibrium conditions, these reactions are isothermal and they are also reversible in nature, which means that whatsoever would be shown to you in this today's session to be happening during cooling in a particular reaction, the reverse of it would happen during heating. Now, with regard to iron carbon systems, there are 3 invariant reactions which occur. The first is called the peritectic reaction, which happens in a high temperature region. Then in an intermediate region, we have another reaction called the eutectic reaction, and at a relatively low temperature region, we have this third and final reaction, which is called the eutectoid reaction. I'll discuss about each of these reactions briefly in this particular session, and I'll take more detail about the peritectic reaction. Again, for your reference, we have shown the iron cementite equilibrium diagram. You see, if we talk in terms of reactions, this iron cementite equilibrium diagram is divided into 3 main regions. This is the relatively high temperature region and is the peritectic region. This composition 0.17 is the peritectic composition, and this temperature 1495 is the peritectic temperature. On a magnified view, this region has been shown over here. Then this intermediate temperature region is called the eutectic region. 4.33% carbon is the eutectic composition, and 1147 happens to be the eutectic temperature. Then this relatively lower temperature region is called the eutectoid region, has been shown here on a magnified scale. 0.77% carbon composition is called the eutectoid composition, and 727 degrees centigrade is the eutectoid temperature. Interestingly, okay, here in this diagram, A, B, C, D shows the liquidus line. Then we have also marked the solidus line, and we have also marked importantly these 3 uh, points: peritectic point, eutectic point, and the eutectoid point. Okay, so let us first start our discussion on the peritectic reaction. You see, peritectic reaction takes place in a lot of material system, and whenever in any material system this reaction takes place, there is a journal format which this reaction follows. I am discussing with you what would happen during cooling. If you are doing equilibrium cooling of the material system in which peritectic reaction is to occur, as you reach the peritectic temperature of that material system, see, all these values, all these temperatures, these compositions would be specific to the material system which is being considered. So when you reach the peritectic temperature of that materials system, these 2 phases would be present: a liquid phase of some definite composition, a solid phase of some definite composition, and these 2 would react in some definite weight ratio depending upon the material system in which the discussion is being done, and these 2 will combine at the peritectic temperature through the peritectic reaction, and they'll give rise to a new solid phase, which I am here referring to as solid 2. Again, this would also be of definite composition, and its weight would be, this x percentage weight would be the total weight of the 2 phases which actually have participated in the reaction, not their total weight, but their weight in which the 2 have it may be possible that they are to combine in the weight ratio of say 1:10, and presently they are present in the weight ratio of 1:15. They'll only combine in the weight 1:10. Whichsoever thing is present in excess would be present along this newer newer phase. But what amount exactly participates in the reaction of this plus this would be this solid new phase formed. Now, if we talk about the iron carbon systems, this reaction is shown by a small family of steels, which I'll discuss in a while with you. In iron carbon systems, the peritectic temperature is 1495. So all those steels which show this reaction, when they reach 1495 during cooling, they'll always have a liquid solution of 0.53 percentage carbon in them and delta ferrite of 0.09 percentage carbon in them. Interestingly, in steels, liquid solution and delta ferrite join in the weight ratio of 1:4.5, and then this reaction occurs. If in a steel the two are not present in the weight ratio of 1:5, for example, a liquid solution is present beyond that range, so some liquid would combine with all delta ferrite and will lead to austenite, plus some liquid solution which was in present in excess of what was required for the reaction would be seen here along with austenite. Similarly, if in another steel this was present in excess of the ratio 1:4.5, then this would be used to some extent, and excess of this, so all liquid and delta ferrite would combine to form austenite, and whatsoever in excess of delta ferrite beyond 1:4.5 ratio was present would be seen along with austenite as the second phase. Okay, let's go to the second reaction, eutectic reaction. Students, we have already discussed this reaction when we were discussing the type 2 and type 3 binary alloy systems. So this is the journal format to be followed whenever eutectic reaction would take place in a system. Specifically, if we talk about the iron carbon alloy systems, in iron carbon alloy systems, this reaction is not shown by steels, which I'll discuss with you in the sessions to come. Yes, all the cast irons, that is all iron carbon alloys from 2.11 to 4.3 to 6.67 percentage carbon will undergo this reaction. But let's here see that what specifically, which phases and in what ratio form undergo this reaction. So if any iron carbon alloy is to show this reaction as it reaches 1147, which is the eutectic temperature, it will always contain a liquid solution of iron and carbon in it with this amount of exactly carbon in it, and then it would undergo the eutectic reaction and would form two new solid phases. One would be austenite of 2.11 percentage carbon, that is in fact the maximum amount of carbon which austenite can accommodate, and the other would be cementite, which is always of 6.67 carbon. So this is eutectic mixture of eutectic austenite and eutectic cementite, which is called lead burite. Fine. Then we come to the third reaction, eutectoid reaction. If you look at this reaction closely, you will realize this is the solid state version of eutectic reaction, whereas in eutectic reaction, one liquid converts into two solids. Here a solid is converting into two new solids. So we have to have a solid phase, which on reaching the eutectoid temperature will convert all into this new solid 1 and this solid 2, and this would always see both eutectic mixture as well as eutectoid mixture will show you a characteristic lamellar structure in which these two new solid phases would be present as alternate lamella. uh, Fine. If we are talking about this reaction in the iron carbon systems, virtually all iron carbon alloys will undergo this reaction. And how, when any iron carbon alloy reaches 727 degrees centigrade, one of the phases which is present in it is always austenite, which is required for the eutectoid reaction, exactly of 0.77 percentage carbon. It converts through the eutectoid reaction into ferrite and cementite. Ferrite formed would be of maximum possible carbon. Maximum carbon which can be accommodated in ferrite is 0.027 percentage, and we know that happens at 727 degrees centigrade. The other phase formed is 6.67 percentage carbon cementite. So rather specifically, if we want to call, this is called eutectoid ferrite and this is eutectoid cementite, and this mixture is called pearlite because it appears like a pearl under an optical microscope when we try to view it. So students, in this particular session, I will talk more in detail of the peritectic reaction with you. So this is something typical, and please pay attention. Let's try to understand. See, the first question that can be asked is, which of the iron carbon alloys show the peritectic reaction? Now, what's the answer to this question? We know that when we are cooling any iron carbon alloy, in that iron carbon alloy, if liquid of 0.09 percentage and delta of liquid of 0.53 percentage and delta of 0.09 percentage carbon, in simple words, if in an iron carbon alloy, when we are cooling that alloy and when we reach the peritectic temperature of 1495, these two phases, liquid and delta, must be present. You will realize that out of all the iron carbon alloys, if you look at the entire spectrum of x-axis, you will realize that only a small family of these iron carbon alloys, which has carbon between 0.09 to 0.53, only these alloys have these two phases in it, which are required for the peritectic reaction when the alloy reaches 1495. So all steels which have carbon content between 0.09 to 0.53 percentage of carbon by weight will only undergo the peritectic reaction. This is question number one. Question number two, which of these steels from 0.09 to 0.53 which show the peritectic reaction, which of these steels undergo the peritectic reaction completely? Now, the significance of the term completely is that which out of these steels which actually show peritectic reaction, which is that steel in which the microstructure consists of only above the peritectic reaction only of the reactants which are required for the peritectic reaction, and after the reaction the microstructure consists of only those things that we have received through the peritectic reaction. Students, the answer to this question would be 0.17 percentage carbon. See, what do we get through the peritectic reaction? We get austenite of 0.17 percentage carbon. So out of all the iron carbon alloys which show the peritectic reaction, you will realize that it is exactly 0.17 percentage carbon steel which only contains austenite in it after the reaction has occurred. This means that this steel exactly contain liquid and delta ferrite in the weight ratio which would be utilized all in the peritectic reaction. So you can find out the weight ratio of liquid and delta in this 0.17 percentage carbon steel, and I have shown to you in this reaction that they are in this weight ratio, and this weight ratio becomes 1:4.5. So that means whenever peritectic reaction would occur in a materials system, the iron carbon material system, the liquid and delta ferrite will always react in the weight ratio of 1:4.5, and whatsoever liquid or delta may be present in an alloy, but it is this weight ratio in which they will come forward and participate in the peritectic reaction and form the austenite phase. So what does that mean? So this steel, because this undergoes the peritectic reaction completely, right, and please don't misinterpret the term completely, this iron carbon alloy, this steel is called the peritectic steel. All steels to the right of it are called hyperperitectic steels. Okay, here it has been shown more clearly. All steels to the right of it are called hyperperitectic steels, and all steels to the left, but only we are considering those steels which actually go through the peritectic reaction, means any steel which has between 0.09 to 0.53 percentage carbon. If we have less than 0.09 carbon, then peritectic reaction would not be shown. If we have a steel with more than 0.53 percentage carbon, again peritectic reaction will not be shown. So I am now considering that these steels are called hypoperitectic steels. And what do these hypoperitectic steels convey? They contain liquid and delta, but if you look into their microstructure just after the peritectic reaction, just below 1495, you see along with austenite that gets formed by their combination through the peritectic reaction, they also contain delta. What does that reflect? That reflects that this delta was present in excess of that weight ratio 1:4.5. Just for an example, students, consider an alloy in which there is 10% liquid. Consider this alloy, and let us assume that just before the peritectic temperature, this alloy is containing liquid and delta, and when I find out its weight percentage, liquid is 10%, delta is 90%. Now what would happen, this entire 10% will participate in the peritectic reaction, and what amount of delta has to participate? 10 into 4.5, so 45 percentage delta will participate. So 10% liquid plus 45% delta makes 55% austenite. So this austenite is there, but this entire delta has not been consumed. It was 90%. Out of that 90, 45 has been consumed in the reaction, but 45 remains unreacted, that is being shown along with austenite here after the reaction. Similarly, if you take any hyperperitectic steel, after the peritectic temperature, if you look into the microstructure, we have austenite plus liquid. This austenite has come through the peritectic reaction, but this liquid, it means it was in excess, right? So whatsoever was required for by delta for the peritectic reaction, that amount of liquid combines with it to form austenite. The remaining excess of liquid as such comes along with austenite even after the peritectic temperature. So I think you have understood the details of the peritectic reaction. Thank you, students. Thank you for watching. Thank you so much.